Did you know that a Japanese car, or really any gasoline car, turns only about a third of its fuel energy into motion? The other two-thirds just leak away as heat.
That wasted heat goes to three main places. 1. Exhaust loss. The burned gas pours out the tailpipe still scorching hot. 2. Cooling loss. The cylinder walls would melt, so coolant pulls heat out and the radiator dumps it to the air. 3. Friction loss. Pistons, bearings, every moving part generates frictional heat. That 1/3 you actually use has a name: brake thermal efficiency. It's the work taken from the crankshaft divided by the fuel energy you put in. In theory, on the Otto cycle, a high-compression gasoline engine could exceed 60%, but for decades, real engines sat stubbornly around 30%. That 30-point gap escapes as exhaust, coolant, and friction, and the story today is the engineering it took to claw even a little of it back.
The Model T era, around 20%. 1980s electronic injection, around 30%. Even in the 2000s, only about 33%. Industry veterans used to mutter that each additional 1% takes a decade. But in the last 10 years, gasoline passenger cars have quietly crossed into the 40% world. Technologically, these are a different machine. You can feel it in your daily life. Take the Toyota Crown. A 1990s 2.0-liter Royal Saloon got around 10 kilometers per liter on the old Japanese 10-mode cycle. The 2023 Crown Crossover 2.5-liter hybrid clears 22 kilometers per liter on WLTC. The test cycles aren't identical, but in everyday driving, it nearly doubled.
And one more thing. Older cars used to give off that raw gasoline smell right at startup, or when a car next to you mashed the throttle. Modern cars? Almost none of that. Here's the twist. The better fuel economy and the disappearing gasoline smell are actually the same story. Both come from learning to fully burn what we used to dump unburned. Combustion was refined, and as a side effect, both numbers improved together.
The toolbox behind it comes down to 7 core technologies: high compression ratio, variable valve timing, direct injection, strong tumble flow, thermal management, the Miller cycle, and cooled EGR. Today, let's go deep on the 3 most fun from an engineer's view.
First, the Miller cycle. In a normal engine, the piston travels the same distance on compression and on expansion, so those strokes are equal length. In a Miller cycle, the intake valve closes late. Part of the mixture is pushed back out on purpose. Effective compression shrinks while expansion stays full length. Why does that help? Because expansion stroke length is literally the time you have to turn heat into work. Compress short, expand long. You extract more push on from the same combustion. The catch? Torque suffers at low RPM. On a conventional car, it feels sluggish off the line, which is why Miller cycles were rare in mass-market engines. Then hybrids changed the game. Low-end torque weak? Let the electric motor handle launch. Run the engine only in its sweet spot. The Miller cycle, once impractical, finally got the stage it needed inside a hybrid powertrain. A big chunk of the plus 1% a hybrid engine earns is exactly this cycle. Second, cooled EGR. You take some of the exhaust, chill it, and feed it back into the intake. Sounds counterproductive, right? It isn't. The inner recirculated gas lowers peak combustion temperature. Lower peaks mean less knock. Less knock means you can raise the compression ratio. That opens the door to higher efficiency. There's a bonus effect too. Normally, to reduce engine output, you close the throttle plate. That's like sipping through a narrowed straw. The piston wastes work pulling against it. This is called pumping loss. EGR pads the intake with inert gas, so the throttle can stay much more open. Pumping loss drops. Recirculating burnt gas quietly delivers a second wind. Here's a twist. EGR briefly boomed in the 1970s, then died. It was introduced under the U.S. Muskie Act for NOx control. But back then, fuel control wasn't fine enough. Combustion got unstable, fuel economy got worse, and the three-way catalyst showed up and handled NOx on its own. EGR vanished from gasoline engines. It returned around 2009 with the Toyota Prius, now in cooled form, and today it's a leading-edge efficiency tool. A 40-year round trip for a totally different purpose.
Third, and this is the big one, cooling loss. Around 25 to 30% of the fuel's energy leaks through the cylinder walls into the coolant. The piston crown hits over 500 degrees Celsius. The cylinder wall sits around 100 degrees Celsius. As long as that gap exists, heat keeps escaping into the wall. You can't just stop cooling, the cylinder would melt. But viewed as turning heat into motion, every joule lost into the wall is painful. Cut 1% here and you gain 1% in efficiency. The single biggest enemy and the single biggest opportunity. The countermeasure, in a phrase, finish combustion before heat reaches the wall. The longer the burn, the longer the wall has to soak up heat. So you want to burn the charge fast and cleanly in the chamber. The tool is tumble flow, a vertical swirl, stirring the mixture and speeding up the flame front. Then a thermal barrier coating on top of the piston. Heat skips the wall and exits with the exhaust.
The clever idea here comes from Mazda's SkyActiv X, temperature swing insulation. Use a wall material with very low heat capacity. At combustion, the surface spikes hot in a flash. On intake, it cools back down just as fast. The wall temperature breathes with the cycle. No time for the heat to escape, solved by the material itself. This is where automakers worldwide are pouring their engineering effort. Step back from all of this, and the whole thing is a tag team of burn it all and don't let heat escape. Burn it all and no raw fuel leaves, the exhaust gets cleaner. Hold the heat in and efficiency rises, fuel economy goes up. The story of fuel economy and the story of clean exhaust look separate at the start. They meet at the exit. That's what refined combustion actually means.
Back to the question we opened with. 1%. Is that really a big deal? Japan burns roughly 45 million kiloliters of gasoline each year. Trim 1% off, and that's 15,000 tanker trucks of fuel. You may have noticed gas stations in Japan are quietly disappearing. Different conversation on the surface, but the math behind it quietly lines up. And the 60% ceiling the theory promises is still out there. The closer you get to it, the more brutally each 1% costs to find. It isn't just 1%. The internal combustion engine is reaching its final form, right in front of us. That's where I think we are.
Thanks so much for watching all the way to the end. On this channel, from an engineer's point of view, we dig into the everyday mechanisms around us, the ones you thought you knew, but maybe never quite understood. If today's story sparked even a little curiosity, I'll see you in the next video.